Hello, everyone, and thank you for coming. And thanks a lot for participating in the Solar Eclipse QSO Parties and future ham radio related experiments. So, as Nathaniel said, I will be presenting some of the results which we have from the Solar Eclipse QSO Parties of 2023 and 2024 eclipses. And these are the tracks which Solar Eclipse has. 2023 was an annular eclipse. So we had it from the western side going to the east, Brazil. And the 2024 eclipse started from the oceans and went almost close to European sector. The timings were nearly same, around say 16 to 20 UT. If you go back and subtract 5 hours, you will be having somewhat the eastern time of US. Now, what I will be presenting are the results from only a limited data set which utilizes the coordinates of the transmit receive location. So a ham, when they operate, they also report their logs on different networks, PSK Reporter, WSPRnet, or RBN, and that's where from which we get the time of the call, the transmit and receive grid signs, which gives us the latitude, longitude, the frequency over which they talked or their automated stations recorded these communications, the path length between a transmit receiver location, so a grid circle distance between the transmitter and the receiver, and then the midpoint. So essentially the geographic coordinates of the transmit receive locations, the distance between them, and what is the midpoint. Midpoint is really important because, as you know, the ionospheric reflection happens. So if we have the radio wave, it goes up and then reflects back from the ionosphere. So that's where the midpoint. Now, we are blessed with the hams and the science part of it, which combines to form a ham radio citizen science investigations. And for that, we really need all of you who participates in the eclipse parties or the upcoming meteor scatter parties. And that gives us a really good database. And we also learn a lot from you. Like when I started, I was learning a lot about the different modes through which the ham radio operators operate and different signals which we get. So thanks. Now, these are some of the results which we have from 2023 and 2024 eclipse. On the x-axis, bottom side, we have the UT time from 0 to 24 hours. And on the y-axis, we have distance between the transmitter location and the receiver location. It's a great circle distance between the two pair. The color in each panel represents how strongly or poorly they were connected. So the brighter the color, which means the connectivity was much more intense. More hams were connected at this distance. Suppose here, around 2000 kilometers, the connectivity was much more stronger. So many people were able to talk to each other, say within 2000 kilometers around 12 UT at 1.8 megahertz. Now, in the different panels from bottom to top, I give the frequencies 1.8 megahertz, 3.5, all the way up to 28. In wavelength, it is reverse. So the maximum wavelength is at the bottom and the minimum wavelength is at the top. The box highlights the interval of the solar eclipse. Now, if you see, the 2023 solar eclipse was an annular one, and 24 was a total solar eclipse. Now, we expect a total solar eclipse to have a bigger impact over the ionosphere and radio propagations as respect to 2024. And that's what you see from here also. Now, 23 solar eclipse, this, if you are able to see my cursor, yes. So here we have a little bump or increase in the range of communications, say at 7 megahertz. And then that increase is also observed at 28 megahertz. It is also visible at different frequencies. But the range increase or the intensity of the color increase is much stronger if you go to 2024 solar eclipse, which was a totality. Now, it happens at all the frequencies right away from 1.8 megahertz to 28 megahertz, all the frequencies or wavelength bands. A way we approach the data to visualize it better is align all the transmit-receive grid circle distances with respect to the eclipse time rather than the UT time. So now in this figure, the central point is the time with respect to the solar eclipse. And the left-hand side is 2 hours before the eclipse. This is the eclipse totality, and then what happens later. Now you can see it from here, 3.5 megahertz and 7 megahertz, they opened up, or the connectivity increased. So once you were talking to someone at 3.5 or 7 megahertz, suddenly when the solar eclipse came, because of the shadow, the D region got depleted, and the strength of the signal or the range of the communications increased. So you were able to talk to someone who was at a farther distance when the eclipse was happening. And this is what it tells from the data. At 21 and 28 megahertz, it is slightly visible from here, but in a different color scale, I will have more figures which will be more pronounced effects. Now, the data which I showed was taken for the contiguous US, which all of you have participated. We have hams operated around the globe, and maximum around US and European continent. So if we include all the ham data around the globe, we get a second channel of communications, which is mostly below the communications below 4,000 kilometer are within continental US, and the channels which are say 4,000 kilometer and above are US to Europe connections. Now, there was a symmetric response in the US continental with respect to the eclipse. There was an increase and then the decrease. But if you look in terms of the US to Europe context, it is asymmetric. There is no response. Then you have a 7 megahertz response, which means suddenly you were able to talk to European guys during the eclipse. And then there is a blip, and then it comes back. With your experience, you know that in the night or when the evening happens, the channel app opens between US and Europe. But eclipse added a second strength to it, which was happening much earlier. Now, these are symmetrical responses in the lower range and asymmetrical responses in the higher range. But it is not truly the fact. If you look at 21 megahertz, the symmetric response happens even at the higher ranges. So US to Europe is also again symmetric. So there are different behaviors which happen at different frequencies, and that allows us to probe the ionospheric behavior, what was happening in terms of the density. We do that with some modeling. Like, we know that the radio waves, once you transmit a radio wave, it goes to the ionosphere and it can come back. It can reach a receiver through a one bounce, that's it, or it can bounce twice and reach a receiver, or it can bounce thrice and reach a receiver. So these we call multiple hops. So 1 hop, 2 hop, or 3 hop communications. Now, what we did is, we did the modeling of radio propagations between US and Europe, because this is where the maximum ham radio stations are. And the black and red are the transmitters and receivers. We do it with 2 different physics-based models of the ionosphere. They are called SAMI3 and Wacom-X SAMI3. So 2 different models, but giving the same output of the ionosphere. Now, this is in terms of the data bundle comparison, how good we are able to reproduce it, or how the data and model are consistent or not, and which model performs better, what are the inferences we can do from the data, and what informations can we get from it. So here I saw only 7 megahertz and 21 megahertz. On the left-hand side, we have the data. Top panel, bottom panel are same for the data. This is epoch analysis. So central point is the totality. This is 2 hours before, this is 2 hours later. On the top, we have SAMI3 outputs, which is one model. On the bottom, we have the other model output. Now, in the 7 megahertz, when the band opens up, stronger color means the band opens up. It also happens in the modeling part, but for the rays which are coming back a lot higher, say, the apogee of the radio waves is beyond 125 kilometer, which we call E region. So E region, within the E region or up to 125 kilometer, the response is nearly limited to 4,000 kilometer. But the rays which went above 125 kilometer or the F region, say 400 or 300 kilometers, they were the ones which responded here. Now, That's why apogee greater than 125 kilometers. So this response is captured in the symmetry model or in the bottom one, both. Now, if you look at the 21 megahertz, since the frequency is so high, it goes directly to the F region. There is almost no bounce from the E region or below 125 kilometer. That's why my middle panel is blank here. And the right-hand side panel says, okay, there was a depletion in the contacts, which we see from this model output also, and the other model output also performs similarly. So the change in the contrast of the color says there was more activity and then the less activity. Now, I said about this happening with respect to the solar eclipse, but what we noticed from the Ham data, because we had a good number of participation, so the data quality and the gridded or the density was higher, so we could go deeper into it. Now, when we looked at the 21 or 7 megahertz, the examples which I showed, what we saw was the changes which were happening because of the eclipse, they were more pronounced when it was in the later phase, around 1930. This time, the vertical dotted white line. You see the color change here, and you see the color change here, which was not the case for the no eclipse day or the next day. So, the eclipse impact was more pronounced in the later phase, not throughout the eclipse, which is here. The eclipse was from 16 to 20 UT, but the maximum impact was around 1930. If we try to control the model outputs, we can have the model outputs with eclipse and without eclipse, and that can tell us what was happening. Now, on the left-hand side, we have the eclipse scenario, and on the right-hand side, we have the no eclipse scenario. And the top row is the data, and the bottom two rows are two different models. You can see the change in the color gradient, which happens at 7 megahertz, and then a blip. This is captured in the model output also. So this part is represented only in the left-hand panel. This pillar kind of or tower kind of thing appears in the model output of this eclipse, but not on the no eclipse scenario. Since these are controlled runs, so we say this is eclipse only. Now, why it could be? Why the later phase of the eclipse was more impactful than the earlier phase of the eclipse? One of the possible reasons which we argue is, you see this totality, solar eclipse totality, which is with the reddish color, and we see the day-night terminator. The night side is darker, day side brighter. So European sector was already in the evening or nighties, and the, say, New York somewhere was under the totality. Now, this channel of solar eclipse shadow and the evening forms a much broader tunnel kind of scenario where the radio waves or the ionospheric impact is elongated over a longer region, a broader region. And that's why the effects are more pronounced around 1930 when it was in the eastern side. There are changes when it was in the central region also, but the maximum impact came around 1930 when it was here. So this was possible because of the ham radio data and the simulations. What we saw was the lower frequencies, say about 1.8 to 7 megahertz, 160 meter to 40 meter, they responded symmetric to the eclipse. If the eclipse came, the range of communication increased, which you might have experienced. But at higher frequencies, say 14 to 28 megahertz, the range of communication had an asymmetric response. When the eclipse came, 7 megahertz got opened, but 21 megahertz was diminished. If you were operating out those frequencies, you would have experienced it. Now, the range of communications when we have between US and Europe, that shows us what we in the ham sci community we have popular as gray line propagation. So the evening side with the solar eclipse formed an extended region which made the ionospheric more impactful around later phase of the eclipse. And the modeling output and the ham radio data are consistent. We will have more information and more analysis on it. And that's what the results we have. And what I have presented is a very limited data which we analyzed. I used only the coordinates of the ham radio stations transmitter receivers. I did not go into the signal part of it. I did not go into different Doppler receivers. And once we include all of that, the rich data set which ham provide or ham radio operators have can give us wonderful results and understanding and improve our ionospheric changes, response, and both radio propagation. So thank you to all of you and our funding agencies.